Okay, I don't want you to get intimidated here. This is a very long set of slides, but it's very pictorial. It's something you're going to need in grade 10, grade 11 physics, and I think is valuable to you as a citizen. The amount that is testable is a very small fraction of this, and I will make it quite clear. The heliosphere refers to the sun around planet Earth. And the sphere of the sun is considerably bigger than the sun itself. If this is the sun here, the heliosphere extends out to the planet Pluto and beyond. It's basically the energy the sun pours out radiation called the solar wind. The cosmic background radiation is radiation from deep in space. And we can actually tell the radiation from the sun blows outwards, and at a certain point, we actually encounter the wind from beyond. So as spacecraft leave the solar system, there's radiation pushing on them from behind. Then all of a sudden, beyond Pluto, the radiation direction switches. And this area right here, where the direction of the solar wind changes, has been crossed by spacecraft. You can go online and type in Voyager audio crossing bow shock, and you will hear the spacecraft's radios pick up the noise as they left the local environment into deep space. And the sun is huge. That's the Earth. This is just a flare on the sun. It provides all this amazing amount of energy, but it's also very threatening to us. Okay? Without this, there's only a few life forms on Earth that could survive. The sun produces a visible spectrum of light, traditionally called Roy G. Biv, for red, orange, yellow, green, blue, indigo, violet. The problem I have with the spectrum is I prefer the red on the left, and that's the way it's written. Pay attention when you see spectrums presented. Many will put violet on the left, not the red. And so from one textbook to another, the evidence is flipped, but you just have to pay attention for it. But if we look at the spectrum of the sun, what we don't see is all the colors of the rainbow. We see colors missing. And this absorption spectrum we'll get into in astronomy. It's what allowed us to detect the Big Bang. So if these green lines here are missing, these three colors are not being produced in the rainbow, that's definite presence of magnesium. So we can actually analyze the spectrum and tell exactly what the sun is made out of. Now the sun's Latin name is Helios. And the gas helium was discovered as a set of missing lines in the sun's color that had never been seen on Earth when we burned anything. And a scientist said, hey, there's a new element on the sun. It's in Helios, so I'm going to call it helium. And so helium means from the sun, and we eventually found it on Earth too. The visible spectrum is only what our eyes detect. The entire electromagnetic spectrum goes far beyond that. And you're aware of many of these terms. Violet switches to ultraviolet light. But if you go below red, they say infrared, which when you spell it looks like it says infrared, but infrared is how you say it. Blue light is very high frequency light, or what we call short wavelength. And because it's very high frequency, it's coming in very fast, like a high note on the piano, and it can damage tissue. So anything from above the visible, ultraviolet, X-ray, and gamma rays will destroy tissue. It's very dangerous to life. If you go the other way and you go below the red into infrared, you will start to perceive it as heat. And if you keep on going way beyond the red, you get into radio waves. If your eyeball was a meter or two across, you could watch your cell phone glow when it transmitted. That I'm aware of, there are many animals on Earth that can see well into the infrared, but no animal has ever been detected that can see radio waves. Now let's compare the spectrum to a piano. Imagine from radio waves to gamma rays spans the entire 88 keys of the piano keyboard. How much of that keyboard is the visible light, just the middle C. We are so blind that to compare it to a piano keyboard would be like sitting a person down at 88 keys of the piano and finding out that they could only hear one note. Anything lower than that or higher than that, they couldn't detect. So our visible spectrum is a tiny slice of what the universe is pouring out from any object that's hot. Some animals can see beyond, a little bit on either side. That I'm aware of, even the best vision on the planet never extends more than 2 or 3 notes above or below the dead middle of the spectrum. On a piano, low notes don't hurt your ears. Really high notes do. Low frequency, fewer waves come in every second, so it's not as much energy. As you go up and more waves come in every second, more damage can be done. Just try to imagine if these peaks were the sound of a person hitting with a hammer. Well, this is bonk, bonk, bonk. Up here, it's bonk, 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 bonk. Much faster energy is being put in. So this is the difference between the full spectrum and the part that we can see. Now, the sun puts out a very large pulse of visible light and very little else. So this is the spectrum of the sun. This graph is showing how bright it is at that spectrum. So if we go over here to the near infrared, that would be the vision in those night vision goggles. Far infrared would be the ones where you see a person's body glowing, like it's, you can see them in like movies like Predator, or when the police are following someone, you can see their body glowing white as they're hiding somewhere. So the sun actually produces very low levels of far infrared, somewhat higher near infrared, but in the visible light, the sun peaks. It puts out an awful lot of light right here in the blue-green part of the spectrum. And then suddenly, thankfully, the sunlight just drops off in intensity, and only 7% of the light is ultraviolet. 44% of the sun's light we can see. 37% of the sun's light we feel as heat on our skin. But thankfully, only 7% of the sun's light is the burning UV rays. So that's how you read an intensity graph. This will become...
Mr. Neal and Mr. Alexander, please call 258.
Yes, there's just nothing I can do about that. So these intensity graphs will become very important in physics. Now, this is the really cool part, how we're fitted to our environment. If you look, the sun's peak output color is this yellow around a wavelength between 500 and 750 nanometers. That's how long the waves are between the pulses of light. Okay? But you can see the peak right there in the blue-green. Look at our eyes. Our eyes' favorite color is right on the yellow-green. So the sun's brightest color is our eyes' favorite color. And what does this kind of graph mean? What it means is that if I shone a red light of, say, just turned on a red LED and a green LED, you would perceive the green LED is almost 5 times brighter than the same wattage for a red LED. Your eyes love the color yellow-green more than any other color and will see it about 5 times brighter than a red or a blue light of the same wattage. So our eyes were designed for this planet, and that's kind of cool. We developed to love our sun. Next, we'll do the atmosphere.